In the previous section, we discussed cutting planes in the pure integer setting. And now we're going to the general setting and we'll talk about cutting planes for mixed integer linear programming. As we did in the pure integer case, let's recap a little bit the notation that we're going to use in this section. So we will deal with a polyhedron P, which is rational. So it's the set of x and y described by a system ax plus gy less than or equal to P. Moreover, the corresponding mixed integer linear set is the set P intersected with all the x's that are integral and y that are continuous. Generally, we will always assume that A and B have integer entries, and we've seen already that we can assume this without loss of generality. We define also in this case the notation pi. In this case, we call it the mixed integer hull of P, and it's simply the convex hull of all the feasible points in P. So the convex hull of our mixed integer linear set, capital S. Again, from the fundamental theorem of integer programming, we know that pi is a rational polyhedron. We here have a simple example. Here's our polytope P, and in blue we have the mixed integer hull pi of P. In this case, this is a two-dimensional example, and we have one dimension that is integral, so the x is just one-dimensional and corresponds to the horizontal axis, and the y is also one-dimensional and corresponds to the vertical axis, and while x is integral, y is continuous. And so the set of mixed integer points is represented in this case by these vertical lines. In the pure integer setting, we discussed Chvátal inequalities, and so the first thing we should do is to try to define Chvátal inequalities also in the mixed integer setting. We can define them also in this setting, but we will see they're not as powerful. In the mixed integer setting, a Chvátal inequality is defined as follows. It is an inequality of the form Cx plus 0y, just to emphasize that there is no y in the inequality, less than or equal to the floor of D, where the same inequality but with right-hand side D is valid for P and C is an integral vector. If we look at an example in this polyhedron below, essentially the only inequalities that we are looking at are those that are vertical, so such that the corresponding hyperplane is just a vertical line because we must have 0 y. And what we're doing is essentially we're picking this vertical inequality and we're rounding it down. So in this case, we're moving it to the left and we can move it as long as we do not touch any mixed integer point. And this immediately makes us understand why Chvátal inequalities are defined in this form for the mixed integer case. Because if you remember, also in the integer setting, we picked any valid inequality for the polyhedron and then we shifted it towards the polyhedron and we stopped whenever we touched any integer point in the space. And here we're doing exactly the same thing, and the fact that we're taking 0 as the coefficient of y simply follows because if you take any inequality that doesn't have 0y, so for example, let's say an horizontal inequality, then you see you cannot push it downwards at all because it already intersects infinitely many points that are mixed integer. So essentially the only inequalities that you can shift towards the polyhedron are those with a 0 coefficient on y. It's immediately clear from this example that Chvátal inequalities are not sufficient to generate the mixed integer hull of P in the mixed integer setting. In this example, we've seen that Pi is this blue region, and given the definition of Chvátal inequalities, here we are only able to chop off this triangle with an inequality here on the right and to chop off this other triangle here on the left with an inequality on the left. But we will never be able to obtain this facet defining inequality of Pi, this one or this one. Therefore, we will never be able to obtain the mixed integer hull of P. So this brings us to the next class of inequalities that we're going to define, and these are called split inequalities. So to define a split inequality, the first thing we need to define is a split. So a split is a very simple set. It's a set like in this picture here. So it's essentially the convex hull of two parallel hyperplanes that doesn't contain any integral points. So algebraically is the set of points x and y that satisfy Ax strictly between beta and beta plus 1. So this is a little bit different from all the polyhedra that we have seen in this course, because here we're using strict inequalities. So essentially this S is not what we normally call a polyhedron, but it's very similar, and we will see that these strict inequalities will be very useful because we will want to describe Rn minus this set, and this is exactly the union of two polyhedra, the one that is defined by Ax less than or equal to beta, and that defined by Ax greater than or equal to beta plus 1. In this definition of S, we need that A is integral and beta is an integer number. So why are we interested in a split set? So let's pick a polyhedron, P, here it is, and now we see that all the mixed integer points that are in the polyhedron are either on one side of S or on the other side. That's clear because by definition S contains no point that is integral whatsoever. Therefore, any inequality that is valid for P minus the set S is also valid for the mixed integer hull of P. And this brings us exactly to the definition of a split inequality, which is precisely what we said. A split inequality is an inequality valid for P minus S for some split S. The set of points that satisfy all the split inequalities corresponding to a specific set S is the closed convex hull of P minus S, and it can be shown that it is equal to the convex hull of P minus S. So in other words, in this case, we do not need to keep using this closure operation, but we can just focus on the convex hull of P minus S. Note that in this example, we have that the convex hull of P minus S is defined by the original P plus one additional inequality, but that's not generally the case. Generally, we can have many more split inequalities that are needed to describe the convex hull of P minus S. And this brings us immediately to our next question. Can we write the convex hull of P minus S through linear inequalities? And the answer is yes. We can use Ballas union of polyhedra. Once again, here's our set capital S, and the set convex hull of P minus S is simply the convex hull of all the points in P on the one side of the split, so that satisfy Ax less than or equal to beta, union the points in P that are on the other side of the split, so that satisfy Ax greater than or equal to beta plus 1. So this is the convex hull of union of polyhedra, and we can just use Ballas formulation. We create a copy of the original variables for one of the two sets and the second for the other set, and we have that the original variables are the sum of the two. Then we write one of the two sets with variables x1 and y1 and with the right hand multiplied by lambda 1, and same thing for the second set. Then we have lambda greater than or equal to 0 and the lambdas must sum to 1. This is an extended formulation for the convex hull of P minus S. In particular, this implies that the convex hull of P minus S is a polyhedron, and this is because projections of polyhedra are still polyhedra. Great, at this point, of course, we can pick any possible split and construct the convex hull of P minus S. So we define the closure, the split closure of P, obtained by taking the intersection of the convex hull of P minus S for every split S. Let's see an example. Here we have our P, and we have already seen that if we pick this horizontal split, then the convex hull of P minus S is this darker region here, so essentially we're chopping off this yellow region from P. But let's now try to pick instead this vertical split. In this case, the corresponding split inequalities allow us to get rid of this small triangle and this small triangle. And I'm leaving the yellow region just to remember what P originally was. Then we can look at, for example, this other vertical split. In this case, the convex hull of P minus S is very simple because we're able to chop off everything on the left of this line. Then we can pick this other horizontal split, and once again we obtain this split inequality, only one inequality also in this case. Then we could take this one and obtain this valid inequality for the split closure. Moreover, we can take this other split. Note that until now we only saw vertical or horizontal splits, but of course you can take a split with any possible slope. So in this case, you have this new split inequality. You can do this symmetrically and obtain this split inequality. Now, of course, there are infinitely many splits you can pick, but in this case, no matter how hard you try to obtain any more split inequalities for P, you will not be able to. And so, in this case, the split closure of P is exactly this set in gray over here. Now, one question that you might have is, well, why I'm not taking this vertical split here? It seems like maybe it will be able to chop off this triangle and will allow us to obtain as the closure exactly the mixed integer hull, which is this square here in the middle. Well, the fact is that this is not true, because if you take this vertical split, you still have to look at the convex hull of everything in P, which is on the left, and everything in P on the right. And note that on the right here, I have 1 point in P. Therefore, by using this vertical split, I will not be able to obtain any split cut that is not already valid for the original polyhedron P. As in the Chvátal closure setting, once we have defined a closure, we want to apply this closure recursively. And this can only be done if we prove that the closure is itself a rational polyhedron. And in fact, it can be shown that also in this case, if P is a rational polyhedron, then the split closure of P is again a rational polyhedron. And this allows us, as in the Chvátal case, to define the split closure number T of a polyhedron P. And this is again obtained by taking T times recursively the split closure of P. In this case, in our example, the second split closure of P coincides with the integer hull of P. Why? Because in this case, there are no points in the split closure of P that are in this region, and so this split immediately gives you a split inequality for the split closure of P that chops off this triangle, this red triangle, allowing us to obtain the mixed integer hull of P as the second split closure. Note that the same split inequality could have also been obtained by considering this horizontal split. The next natural question we know very well is, do split closure converge to the mixed integer hull of P? Well, we now see a very simple observation that will allow us to conclude that we do have a finite convergence in the pure integer case. And this observation is that every Chvátal inequality is also a split inequality. How can you see that? Well, pick any Chvátal inequality. Remember, we have to pick a valid inequality for P and then round down towards P. And this picture already suggests some kind of split, because in fact, if you round also on the other side, you obtain this other line and you've obtained a split. And if you think about it, the Chvátal inequality that we originally started from is in fact a split inequality for P corresponding to this split. So this observation, together with the theorem 5.1, immediately implies that we have finite convergence in the pure integer case. So this is stated in this corollary. In the pure integer case, if P is a rational polyhedron, then there exists a finite number T, so that the split closure of P number T is equal to the integer hull of P. But what about the mixed integer setting? Well, it turns out that in the mixed integer case, in fact, split inequalities are not sufficient to generate PI in a finite number of iterations. We will not be proving this, but I want to give you the idea of the example that allows us to prove such a statement. This is the example. So this example is in dimension 3. We have two integer variables and one continuous variables. So this is a pyramid. Let me start with this picture over here. Here, this is a two-dimensional picture. In fact, I am observing my pyramid from a point of view that is above the pyramid, and it's essentially orthogonal to the x space, the space of the integer variables. So from above, I can see all my pyramid, and the base of the pyramid is the triangle that is the convex hull of the origin, the point 2, 0, and the point 0, 2. And then in the middle of this triangle, I can see the ridges of this pyramid, which are going upwards towards me, and the apex of this pyramid is exactly at the intersection of these three segments. So maybe now we can understand this three-dimensional picture. This is a somewhat isometric picture, so I see the x1 axis, the x2 axis, and then the vertical y-axis. Earlier on, I was observing this pyramid from above, somewhere here. So as you can see, the base is, as we saw already, the convex hull of the origin, the point 2, 0 in the x space, and 0, 2. And all these 3 points have a y equal to 0. So this is the base of my pyramid. Then the apex is a point that is somewhere you see in the middle with respect to the x space, and then it's lifted higher. So it has a y component that is strictly positive. And so that's how my pyramid is. It's just a convex hull of the 3 points in the base and this apex. Now, in this picture, these vertical pillars correspond to the mixed integer points in my space. As you can see, these mixed integer points only touch the pyramid on the boundary. And all the points in the pyramid that are mixed integer have a y component that is equal to 0. And this implies that the mixed integer hull of this pyramid is exactly its base. Great, so now let's look at the split inequalities. So the fundamental fact is that no matter how hard you try, any split that you can find will never fully contain P inside it. This means that there's always a point in the pyramid that is outside of the split and that has height, so meaning the y component, strictly larger than 0. Therefore, whenever you take the convex hull of everything that is in P and outside of the polyhedron, you will always obtain some strange looking set, but what is important is that such a set will always contain a pyramid of the same exact shape as this one, but with an apex that is with the same x1 and x2 components, but with a lower height, so with a lower y component, but always strictly positive. Therefore, when we take the split closure, we take the intersection of all these smaller pyramids, and we want to argue that such a split closure still contains a pyramid looking exactly like this one, but with smaller height. And of course, you can see that repeating this argument over and over again will show that you will never obtain the mixed integer hull of this polyhedron, which consists of only the base of this polytope. Now, there's one more thing that we need to check in order to be able to actually convince ourselves that the split closure still contains a smaller pyramid. In fact, what is the problem? Why haven't we really shown it yet? Well, this is because the split closure is the intersection of potentially infinitely many sets conv p minus s. So even though each one of them contains a smaller pyramid, we could have that the limit of these heights of all these pyramids goes to 0, and the intersection of all of them becomes exactly the base. But this cannot happen, and in order to understand that, one just needs to be a little bit more careful when proving that any set conv p minus s contains a smaller pyramid. In fact, what one can show is that every set conv p minus s contains a smaller pyramid with apex with height at least 1/3 of the original height. And so in this way, the limit cannot go to 0. All these sets conv p minus s must contain the 1/3 of the original pyramid, and so also their intersection must contain the same pyramid. Great, so I hope I could give you a little bit of the idea on why split closures will not always converge in a finite number of operations to the mixed integer hull of the polyhedron. Now, the good news though is while we do not have a finite convergence, we do have infinite convergence. What does it mean? Well, it means that with split closures, maybe we will never be able to obtain exactly the mixed integer hull of P, but we will be able to obtain a set as close as we want to the mixed integer hull of P. We just need to take a sufficient number of split closures. So formally, here is the statement. For every rational polyhedron P and for any epsilon greater than 0, that is that in a sense represents how close we want to get to the mixed integer hull, there exists a finite number T so that the split closure of P is contained in Pi plus a unit ball of radius epsilon. This is a fairly advanced result and we're not going to show it. However, this gives us essentially the limit of what split closures can do. So the next question is, can we obtain also in the mixed integer setting a finite convergence result? Of course, we've just understood that with split we're not able to do so, so we need to use a different type of inequalities. The inequalities that will give us finite convergence in the mixed integer setting are called lattice-free inequalities. So let's start by defining them, and as we did for split inequalities, we first define lattice-free sets and then based on that lattice-free inequalities. Lattice-free sets are very similar to split sets. They are sets defined by strict linear inequalities in the X space such that they don't contain any point which is mixed integer. So the definition is very similar to that of a split. The only difference is that in the case of splits, we only have two inequalities with a very specific structure. Why are lattice-free sets useful? Well, exactly for the same reason for which split sets were useful. Pick any polyhedron P, and now, by definition of lattice-free set, every mixed integer point in our polyhedron is in the set P minus L. Therefore, we define lattice-free inequalities as any inequality valid for such a set. Clearly, they are valid for the mixed integer hull of P. Like in the split case, it makes sense then to consider the intersection of all lattice-free inequalities for a specific lattice-free set L, and in this case it is the closed convex hull of P minus L. Here there's a little difference with respect to splits, because in the case of splits we saw that the closed convex hull can actually be equivalently replaced by the convex hull, and in this case, so this is not the case, and so we're forced to keep using this closed convex hull. So, as we did for splits, the question is, can we describe the set closed convex hull of P minus L through linear inequalities? And the answer is always the same. We can again use in the same exact way Balázs theorem to obtain an extended formulation for such a set. The only difference is that now this set is the closed convex hull of the union of not just two, but still finitely many polyhedra. So we write again the extended formulation given by Balázs. We create one copy of the original variables for every region. In this case, there are k linear inequalities defining a capital L, so we have k copies of variables. The original variables are the sum of all the copies, and then we write every region with a copy of that variable, and with the right hand multiplied by lambda I, and then we have essentially convex combinations on the lambdas, so lambda greater than or equal to 0, and sum of the lambdas equal to 1. This implies that the closed convex hull of P minus L is a polyhedron, since it's just the projection of this set onto the original XY space. As you can see, we are following step by step what we have done with the splits. So, I guess you now expect me to define the lattice-free closure and then analyze if such a closure does converge infinitely many iterations to the mixed integer hull or not. Well, it turns out that we don't even need to do that. In fact, if we defined the lattice-free closure of P, it would be exactly this definition. It would be the intersection of the closed convex hull of P minus L over every lattice-free set L. However, in this case, one can show that this intersection is already the mixed integer hull. So this is good news in the sense that we do obtain finite convergence, but this result seems to be a little bit trivial because in fact the very first closure is already equal to the mixed integer hull. In fact, this is a fairly simple result to prove. We're not going to see the proof in details, but the idea is very clear and very simple. Essentially, here's your polyhedron P. Pick any inequality valid for the mixed integer hull. In this case, it's this vertical line, and the direction of the inequality is of course left. And now what I need to show you is that this inequality is valid for the closed convex hull of P minus L for just one specific lattice-free set L. From the picture, it's kind of clear that we should take as the lattice-free set exactly what is chopped off by the inequality, which in the picture is this triangle, which is a lighter shade of gray. But if you actually think for a minute about this, this is not correct. Why? Well, because we need to look at the closed convex hull of P minus L, but remember, L is a set defined by strict inequalities. Therefore, the set P minus L still contains all the boundary of the original P. So the closed convex hull of a set that contains the boundary of P is clearly P once again. So this is not a correct proof, but it's the right idea for a proof. In fact, everything we need to do is enlarge this lattice-free triangle just a little bit so that we bring these two edges of the polyhedron in the interior of the triangle. So in the picture, we just enlarge the triangle in this way. And everything we need to check is that we can always do it while keeping the set lattice-free. So we're not, of course, allowed to have any integer point inside the triangle, but this can be easily shown that is always the case, and you can always enlarge such a lattice-free set in such a way that the inequality you started from is indeed valid for the closed convex hull of P minus L. So is this it? Are we satisfied with this finite convergence result? Well, we're not. The first reason is that this result is very simple to prove. Well, it's not that we're only interested in results that are hard to prove because we're masochistic, but the fact is that if something is very simple to prove, it means that it's not very deep. The second reason, and I would say the most important reason, is that this family of lattice-free sets is not minimal, meaning that we do not really need all of them to obtain finite convergence. So why do we care about this? Well, from a practical perspective, we're interested in this type of results because then we know that we should use lattice-free sets to obtain cutting planes for P in order to get closer and closer to Pi. And everything we're saying with this result is that, yeah, we can get PI, but the choice of lattice-free sets that we have in order to obtain it is just too vast, it's huge, and essentially it will be very difficult to obtain a good lattice-free set to obtain a good inequality for PI. I know this is very hand-wavy and I just want to keep it at this level. Just to give you an idea, let me go back for a second to the previous picture. Now here, essentially what we want to obtain is a strong valid inequality for the mixed integer hull, which is this vertical inequality. And in order to do so, we want to use lattice-free sets. But in this case, guessing this triangle, which gives you this inequality, is as hard, if not even harder, than guessing the correct inequality for the mixed integer linear set. And essentially you can formalize this reasoning and understand that there are simply too many lattice-free sets to be useful from a practical perspective. So the next natural question is whether we can identify a set of lattice-free sets which is as small as possible while still giving us finite convergence. The point of departure is clearly understanding if there are some lattice-free sets which are necessary in order to get finite convergence. And what can be shown is that a class of lattice-free sets that are always necessary to obtain this finite convergence is the class of lattice-free sets that have integral vertices. Of course, talking about vertices in lattice-free sets which are not polyhedra is not entirely correct, but here I don't want to be too formal, and when I talk about a vertex of a lattice-free set, I really mean a vertex of the corresponding polyhedron obtained by replacing the strict inequalities with inequalities of the form less than or equal to. To prove this proposition, one essentially has to mirror the construction that we have seen in example 5.11, where we saw that for the pyramid in R3, split inequalities are not sufficient to achieve a finite convergence. Of course, not all integral lattice-free sets are truly necessary. I need to focus on the maximal ones. This is a bit of a technicality which I hope will not get you confused. The fact is the following, that among any family of lattice-free sets, you can always just consider the maximal ones. Essentially, you can always throw away all the ones that are not maximal, because if you have two lattice-free polyhedra and one is contained in the other, then the smaller one, you can throw it away because every inequality that it gives can also be obtained with the larger lattice-free sets. And this is an easy observation to check. So at this point, we know that all maximal integral lattice-free sets are necessary. The question is, are they also sufficient to get finite convergence? And the answer is yes. So let us now consider integral lattice-free inequalities. The first thing we want to do is now define the closure obtained only using these lattice-free polyhedra that are integral. Therefore, we take the intersection of the sets closed convex hull of P minus L only for such lattice-free integral polyhedra. Here we have a couple of examples of lattice-free integral polyhedra. So this we know very well, it's just a split. Therefore, the integral lattice-free closure in particular is smaller than the split closure because we're intersecting also all the sets corresponding to the splits. But on top of that, we have many more lattice-free integral polyhedra, and this guy here on the right is an example. As you can see, this is a triangle with the vertices integral and lattice-free. In particular, it's also maximal because it's not contained in any split. And this triangle should remind you of the example that we've seen, which showed that split cuts are not sufficient to generate the mixed integer hull in a finite number of iterations. And if we apply this triangle to that example, you will immediately see that we obtain the mixed integer hull. So for that specific example, the integral lattice-free closure of the pyramid is the mixed integer hull. Also note that these are just two examples of lattice-free integral polyhedra. Of course, there are many more, but these are the only ones that we can visualize in dimension 2. Furthermore, of course, you can also take any affine transformation of both these sets and obtain other lattice-free integral polyhedra in the plane. Also in this case, like for the splits, one can show that if P is a rational polyhedron, then the integral lattice-free closure is again a rational polyhedron. However, it's not generally true that the integral lattice-free closure is equal to the mixed integer hull. So we might need several rounds to obtain the mixed integer hull. Therefore, we define the integral lattice-free closure number t for any natural number t, and it's simply defined by taking recursively t times the integral lattice-free closure of our polyhedron P. We're finally ready to state our finite convergence result. If P is a rational polyhedron, then there exists a finite number t such that the integral lattice-free closure number t is equal to the mixed integer hull. So this theorem serves as an analog of the result about Chvátal closures for the pure integer case. We have also discussed a few slides ago how all maximal integral lattice-free sets are necessary in order to obtain finite convergence. Therefore, this result is tight. And this concludes our video on cutting planes for mixed integer linear programming.